Okay. The parametric curves for the circle, as we've seen in previous sections, are x equals cosine t and y equals sine t, and t being the parameter. For the Euler spiral, the parametric curves are a bit more complicated. X equals ft and 0, cosine u squared times du, y equals ft and 0 sine u squared times du, where x is the parameter and u is the arbitrary variable name. As can be seen from both of the figures, both of the parametric curves are different. Therefore, a vehicle or a bike having the parametric curves of displacement will be having different velocity and acceleration curves. Let us plot this curve in GeoGebra. Remember the Euler's method. First try to integrate the cosine and sine curve with the help of the Euler's method, or you can also make a slider and let GeoGebra do the rest for you. In both ways, the integrated curves are the same. Okay.
Okay, any problem here?
No. Should I graph it then? Like
Yes.
yes. Okay.
Let's
So I do the cosine and sine graphs. Or
X is
X, okay. Okay.
okay now.
So they start off with the big periods, like very long periods, and then as time goes on, the periods become smaller and smaller and closer together.
Yes.
And then same on the negative side. Well, the negative side, it starts out very small periods and then it goes into larger periods until
the period like it
yes.
So if you are gonna draw the shape out of the curve,
I think it would be, well, I mean, I know what it's going to be because it's here, but I think it makes sense that it is like the curve is very continuous and it's not just a full circle. Because the periods are getting smaller and smaller, that means that the radiuses of the circle are also getting smaller and smaller, which means that there's a sharper turn, or there's a smaller turn, or I guess sharper turn, depending on how small the radiuses become for the circles. So it would give sort of a looping sense if you were to graph the
yes, the cosine it would be like this.
Yes. And so I think that's why it becomes like a big, very big curve, and then it goes smaller and smaller and smaller.
Yeah.
Okay. Go to the next slide here. Okay. First, take a look at the curve cosine x squared, and then divide it into equal parts. Place one point or edge points in the figure in the mid of each interval. Now, as described in our first section of the Euler method starts finding out the slope and start arranging the line segments. In the third figure, so many of these line segments have been placed, but there is still one thing left to do. Can you guess what this is? I guess just finding the the slope and area.
Divide.
Okay.
They have arranged them according.
Okay. Wait, sorry, can you repeat it one more time?
Okay, so there is Euler's method to do the integration. Do you remember in the starting classes, we did differentiation and integration by this method?
Yes.
We took slope and and then we differentiated a sine curve.
Yes.
We took slope that we plotted against. We are plotting against time. It is.
So, okay.
So here we are supposed integration.
Right.
Basically, they are doing by Euler method, like how you do.
Okay. So, should I also put the lines on the here on the graph as well, like it is here?
Yes, so it is this. Can I do it for Euler's method? Next, or when I just write the integration command input.
I can. Oh yes. And then this one.
Yes.
Okay. And then the function will be cosine x squared. Oops, x squared, and then the starting would be is 0. And then the other side would be endpoint would be.
Okay. Let's make the slider.
Oh, okay, right.
And the range is fine if it's.
Okay. And then I'm gonna do
Okay, so what these curves are showing?
Oh my gosh. They're okay. They're showing the like where the slope is going, I guess, for each of the. Hmm?
Okay, what is this A and B? What they are showing? Can you move the slider and look?
Yes. I think A is showing the. Okay, A is showing the slope of both, like the.
What is integration?
Oh wait, no, sorry. And the A is showing um um
You can.
no, sorry, I know this. Let me think about it. It's the like the area of the curve, I guess.
Yes, yes. Area under the curve.
Under the curve, under. So that's what the A is. Or that's what B and C are showing, I guess. The
Yes.
area under the curve.
And the range are from.
The range is from -5 to 5. I guess the range of the interval is from like 0 to A, so -5 to 5.
Yes. So it is 0 to 0.5 right now.
Mm-hmm.
So you can actually hide one area and you can look the other area.
Okay. Um, since we're watching it, is it like 5 a.m. there? I just checked the time. I'm so sorry.
Oh no, it's
No, it was so late there. I'm so sorry. I
oh
could
no,
have been at night too.
it's completely fine for me. Like I wake up at.
Oh, okay. Okay. That's good actually. That's a good
Yeah,
habit.
because my like everyone has to pray Fajr and
Oh, the best. I'm not good.
that's why there is no like sleeping if I'm not even taking the class. Like I won't even.
वापस से आप सोने वापस नहीं जाते आप बस you just stay awake.
Because actually I have two nephews and they are quite like they are quite little younger, so they
Hmm.
don't sleep, so they
Oh,
don't let the
अच्छा
whole family sleep.
आप कैसे सो सकते हैं? अच्छा अच्छा क्योंकि मैं सोचती हूँ फजर के बाद मैं तो हमेशा सोती हूँ.
Yeah.
Hmm.
So like they don't let sleep, so we just and then after a few like after 2 hours, like after just at 6 o'clock, so everyone starts getting up for they start like preparing for the school, and
Hmm.
so everyone start doing. They have their own commitments. So after like getting up, Mama starts doing tilawat, and so no one sleeps, and then after 2 hours we just start
Hmm.
getting or whatever our commitments are for that.
Right, right.
Yeah, so it's that's completely fine.
Hmm. अच्छा अच्छा तो फिर um
Yes, so now you can see the area under the curve, and that curve is sine of x squared.
yes.
Okay, and now you can see that it is from 0 to 5, and The area which is being shown here is under the cosine, is under the sine curve.
Mm-hmm. Yeah.
Similarly, you can see the area for the other curve also.
Yes. Mm-hmm. Okay.
Yes.
Mm-hmm.
So now you can open the trace of both of these points B and C.
Mm-hmm. Oh, I guess there is no trace. Mm-hmm. Um,
Do we have trace here?
no, I think it's just show object. Let me check. It's not even भी नहीं है.
Um,
Change कर सकती है, but that's it. Yeah.
oh, why there is no. 1 minute. Can you play the slider now?
Mm-hmm.
Okay, yeah, I got it. We have to make point out of it, and then we have to open the trace of that point. Okay, so
Okay.
our slider is A, so we
Mm-hmm.
will plot this integration against our slider. So it would be B comma A, and the next point will be C comma A, and then we have to open the trace.
Okay. Oh, this is so interesting.
Yeah. Okay, but I guess so we need to plot.
Wow, this is so cool.
Okay, so these are actually the parametric curves for Euler spiral. So we are plotting area against time, right? Okay,
Yeah.
we need to make a little bit changes in our a little bit change in our points. So stop the slider.
Okay.
So right now it is like towards the y. It is more like towards the y-axis. We want to plot it on the x-axis. So we will change it, like we will first make in our points. If we want to change it, like we want to have this thing on x-axis, not y. So what we
Mm-hmm.
were supposed to, like, whatever this pattern is making up, it's more kind of a going in the y direction.
Right.
So we want it for the x direction.
Um, I guess instead of taking the curve or the area under the curve, you take the um,
No,
hmm.
no, we have to take
Oh,
the area to the curve.
okay, right.
We just want to like shift it to the y-axis. Right now it is sorry, x-axis. Right now it is kind of a um closer to y-axis. We want it for the x-axis.
Okay. Okay. Hmm. I guess you could do it in the
What changes we need to make in point?
Oh, wait. Oh, I guess you could just switch A and B around, like.
Yes, yes, very good.
And then, uh-oh. I just like did this. Yes, okay, perfect. And then this one.
Okay, so did you play the slider now?
Okay. Let me like.
Hmm. Yes, no, it's fine. Okay, can you now see what is the difference in the curves of sine of x squared and cos of x squared and these new integrated curves which we have met? Also, you can increase the range of the slider from -10 to 10.
Okay.
Now play. Okay, yeah. So now what is the difference in between of these integrated curve and the sine of x and cos of x?
Well, the integrated curve has like. Wait, sorry, could you repeat it? It cut out.
I'm saying what is the difference in between of them, like the
Oh,
integrated curve and the other ones.
the sliders. Okay. I guess the integrated curve has it's bigger. The periods are bigger. Or not the periods. Sorry, the altitude. I think. What is it called?
Yes, yes, the altitude, the
Okay.
amplitude.
Okay, yeah, the altitude is bigger. Um, and but like the periods are the same, or they're roughly the same. They're roughly the same, but the altitude is bigger for the integrated curves than it is for the x, a, and b points.
Okay,
And
so
yeah,
this A and B points are the trace of the integrated curve, right?
right.
And the sine of x and cos of a square curve is what we are seeing.
Mm. Oh, okay. Okay.
Okay, so in sine of x square and cos of x square, our amplitude is same, only the period is changing, right?
Right.
But in the integrated curve, our amplitude is getting smaller as well as our
Periods are getting smaller as
yes,
well.
as well as our periods also. So
Mm-hmm.
both of these
Are
um
getting smaller,
yes,
like the
both
both
are like
effects.
what the factors are decreasing at every moment. So what do you think? Which are actually the real parametric curves for the Euler spiral? The integrated ones or this cos of x square and the sine of x square?
I think what's the difference just between the two of them, right?
My voice is not clear.
No, for some parts it is, for some parts it isn't. But
Okay. So I'm repeating my question. My
okay.
question was that
Mm-hmm.
what do you think which curves will make the Euler spiral?
Oh, okay. I think that I'm gonna pause this. I think that the I think the A and B, I guess integrated points will make the Euler spiral. Or actually. But it said that the formula for the Euler spiral was these two. So wouldn't these two make up the Euler spiral?
Yes.
Okay.
So why? Like just because as we see in the Euler spiral,
Mm-hmm.
the radius is getting smaller, right?
Right.
And also we know that if the radius is getting smaller, so the time period is also getting smaller, right?
Yes.
So
So.
radius depends upon the amplitude of the sine and the wave, sine and the
Mm-hmm.
cos.
Mm-hmm.
So here the amplitude in which, and we know that our amplitude is also decreasing. So it means that we have these curves. The integrated curves will make the Euler spiral. Okay.
Okay. So these ones then, like
Yes.
the formula, but these ones. Okay, that makes sense. Yeah, actually, because. Hmm.
Yeah, because
Because I think, well, obviously, like you said, the radius gets smaller, and then the time also gets smaller. Or so the these integrated what's it called, curves actually show the fact that the time gets smaller, whereas with these, only the period gets smaller. I guess these don't really show like that amplitude getting smaller, the radius getting smaller, but the integrated ones show both radius and time getting smaller.
yes. Okay.
Mhm.
So
Yeah. Okay. Um.
so now should we plot? Should we make the Euler spiral?
Um. Yeah.
Okay. So
Yes.
what do you think? What we need to do to plot the Euler spiral?
We need a parametric
Yeah, the
variable.
integrals are the parametric curves for that.
Mm-hmm.
So how do we plot parametric curves so that we can plot the shape?
Yeah. Um. We would first get connect the line segment, I guess, to a slider, and then you just move the slider and you take whatever point is on these graphs, and you put that point for the y or for the x-axis. Or no, sorry, you put the parametric point for the x-axis, and these points. I guess. Okay, wait, sorry. So for sine, you would put the x-axis, you would have the sine be the x-axis, and the parametric, I guess, variable be the y-axis, and then for cosine, you'd make the parametric variable the x-axis, and the cosine variable the y. I think if I remember it correctly. Actually, wait. Actually, let me let me try to remember. Um, wait. Actually, okay. Wait. No, I think I do have it right. I think I.
Okay.
Okay. Sorry. I think it is the y is equal to the cosine, and the y is equal to um.
Okay, that doesn't matter. You can take any point anywhere, like to make it.
Okay, that's true. That's true. But okay, so then should I just start plotting it, I guess? Okay, let me get the
Yeah, so how we're gonna plot a shape out of parametric curves?
mm, I guess you just put the variables together.
Yeah.
Okay, so let me start with number one. Okay, I'm gonna start. Okay, so I'll just start 0, comma 0. Okay, and then I'm going to do the cosine first. Wait. Okay.
Okay, so you're gonna plot each point one by one. Now you
Um,
just plot like a
oh,
single
you
point
could
and
put the
uh, get the trace out of it.
no. You could do just like x equals a a, and then you could just do it like this, I guess, and then have. I guess you could say wait, okay. It's like okay. Um, and you could just do x comma or I guess not x big eq comma b. And, okay, wait. Let me try to remember how I did this.
Okay, look through the slides.
Okay. Mm. Whoa. Wait. Okay. Okay. Point the plots of the integrals against m. Color them as you like. Okay. Okay, well, we did that, and then final step, make a point out of A and B on the resting group. Oh, okay. I see what I did wrong. Okay. Okay. I hope that is. Is this like right? Let me see. Hmm. Oh, okay. Wait. Okay, sorry. Caps. Okay. Hmm. Oh, wait, I did the wrong. Wait. Okay, wait. Okay. Okay, I did it. Finally. But I did it. Oh my gosh, it goes so small. It goes
Yeah,
so
it's
incredibly
getting
small.
smaller and
That
smaller.
is so crazy. Okay. Should I go to the next slide, I guess?
Okay, so yes, you can go to the.
Okay. Oh. Oh my gosh. Okay. The pink curve shows the linear increase in velocity as compared to the quarter circle where it remains constant.
Okay, so it is the velocity being plotted of the
Uh-huh.
either span.
Mhm.
And look how the velocity is increasing.
Yes. It just keeps going and going and going. And then the brown curve shows the linear increase in acceleration. Okay, so the linear increase in velocity is much higher than the increase in like velocity, I guess. Or it's much more together, I guess. Or it's in a constant, like.
It's more in velocity while the less in acceleration.
Yes.
Very acceleration meaning. But
Yeah.
compare the acceleration here
Mm-hmm.
with the acceleration of the circle.
Mm-hmm. Okay.
So here the acceleration is like reducing, while there it's like so here the acceleration is changing gradually, while there it like started like it becomes infinite at very easily, right?
Mm-hmm. Right.
So that is but for the Euler spiral, I guess the Euler spiral section has completed now.
Okay. Um, okay. Oh, it's just this. Physical significance of the Euler spiral. A smooth transition in curvature. The Euler spiral provides a smooth and gradual transition between curves of different radii with different radii of curvature. This is particularly important in road design and railway engineering, where abrupt changes in curvature can lead to discomfort for passengers and excessive wear and tear on vehicles and tracks. The Earl spiral helps ensure the transitions between curves are gentle and contagious, enhancing safety and ride comfort. Reduced G-forces. In transportation, especially for vehicles like trains or cars, abrupt changes in curvature can lead to high lateral G-forces, which can be uncomfortable or even dangerous for passengers. The Ural spiral allows for gradual changes in curvature, reducing these G-forces and making the ride smoother and more comfortable. Signal design. The Ural spiral is used in signal design for highways and railways. Its smooth transition properties are crucial for ensuring drivers and train operators have adequate time to respond to upcoming curves or changes in direction. It helps in designing road signs and signals that provide timely information to drivers and promote safe driving practices. Okay. Bridge design. In civil engineering, the Ural spiral is used in bridge design, particularly for determining the optimal transition between the straight railroad, roadway, and the curved sections of a bridge. This ensures the vehicle can smoothly transition onto and off the bridge without encountering any sudden changes in curvature. Physics and optics. In physics and optics, the Ural spiral is used to describe the gradual change in the phase of a wavefront, which is important in the study of diffraction and wave propagation phenomenon. Its gradual curvature changes the properties, making it a valuable tool in ensuring smooth and safe transitions in a wide range of fields.
Yeah, so it was all about the Euler spiral.
Mhm. Yeah, it's
So,
very interesting.
um, so do you know about what should we start next? Should we go towards the applications of integration or differentiation, or should we go towards the complex or imaginary numbers?
Um, can we do complex and imaginary numbers?
Okay, so we can go towards that as well. So, and also the next section of the book is also the complex and imaginary numbers. So,
Okay.
yes. And so, what do you think? Like, right now, I am asking you this question right now. and then I will ask the same question when we will complete this section, the complex and the imaginary numbers.
Uh-huh.
So, yeah. So, my question is, what do you think or feel right now about the complex and the imaginary numbers?
With complex and imaginary numbers, I do know them and I know them. I think I might be just like a little brushing up, but I know them. But then I think I feel confident in them. Like I know that I
Not
is equal
confident,
to
but not
root.
like um
Like,
I'm asking like, what do you think by their names, like what they would be, like what they
oh,
would.
okay. Oh, sorry. I just sorry. Okay, complex numbers I think would be numbers that have okay, imaginary numbers. I know what they are. It's like it's like negative. It's root negative one. Root negative one can never happen because there can never be a negative one underneath a root square. Well, because it doesn't make
Yes.
any sense. Because if you were to square negative one, it would just turn into one. So when you unsquare things, you're only going to get the positive of that. Or sorry, when you square root numbers, you're only going to get the positive number of you know, for
Yes.
the squares. So with root negative one, it makes no sense. That's why people say it's imaginary, I guess. So that's what an imaginary number is. Or that's what I think it is, I guess. And then a complex number is just like it is a number with an imaginary number. I'm pretty sure. That's what I'm assuming it is. Because making it's I guess not just like a regular number anymore. Like for example, it's like 2 plus 3i. Like that would be a complex number because it's not 2 plus 3, it's 2 plus 3i. So you'd have to, it's a very complex way of thinking, I guess. That's my,
Okay.
that's
Okay.
my
Okay.
thought process.
So, what do you think? Why we need them? Like, why we need them for the first place? In the first place, why we need to invent such kind of numbers, and like, what is the reason or what they actually do? Is
Mm,
are they like just imaginary, or there is any physical significance to them as well?
I guess I think they're imaginary because they give us the solution to equations that we don't know the answer to. Like that, I guess not, now we don't know the answer to, but that we wouldn't have any real number solutions for. For example, like if I had to do like negative, let's say negative like 9,
So, except
I
finding
don't.
the solution to the equations,
Mhm.
okay, so is there any other significance to them also?
Um, I don't think so. Like I think it's
Okay,
like
yeah.
because we need something. I think it's just we needed something to be like to answer our problem, so we made an imaginary number.
Okay, so there is no physical significance then we just where we are not able to solve our problem, we take imaginary numbers and we just try to solve like okay, so maybe we
Mm.
can solve it in imagination if we are not able to do it in real.
That's what I think at least. That makes sense to me. I don't
Okay,
think that there's any like.
okay, so that makes feel sense to you.
Hmm.
So, okay, your response has been nodded.
Okay.
Okay, so now I'm gonna ask the same questions from you when we are gonna done with this section. Okay,
Okay. Okay. Got it.
so yeah, I guess so. The only the 5 minutes are left for the class. So
Mm, so should
yeah,
I
you should move
finish
to the
reading?
next slide.
Uh, the Euler formula. Euler's formula is considered to be one of the most beautiful, profound equations in mathematics, and Albert Einstein appreciated it very much.
Okay, So actually, basically, the book is about a scientist, a mathematician
Mm-hmm.
named Euler Leonard. Okay,
Mm.
so the Euler Leonard has made a lot of contribution in mathematics. Like he just published 800 mathematical research. Like he published 800 papers
Oh,
on
wow.
mathematics. Yes. And he solved many mysteries which were out there from the time of uh, like and like they were there for like thousands of years, and then Ehlers jumps in and he just solves those problems, and he have made such a profound discoveries or mathematical tools that we, even in this time when we have such advanced engineering, and we are doing it on the GeoGebra. And remember that that guy doesn't have any such tool, the GeoGebra. So he was such a genius. And he was like, and also he was blind.
Oh, wow.
Yes, okay. And I'm sending I will pin I will send you a link of a YouTube video that is about the Euler Leonard, and it is such a good like documentary on him, on his life. So if you will get a chance to watch that video, so you can watch it. And if you didn't get a chance, so we will like have it at one day in our workshop. Okay, so but
Okay, I will
if
try
you
to watch
if
it.
you got a time, or so you can watch it yourself. But it is such an amazing, or it's a good like documentary on him, on his life basically. So like it's necessary to watch that, so we can plan it together as well. So
Okay.
okay, so but the Euler was actually one of the mathematical genius. It is one of the person who like it is one of the person who born in 100 years, like one in 100 year. That is a person he was. So
Oh, wow.
the same he met this Euler. So basically we first, the first section of the book is about Euler's method, like how according to the Euler's method we can differentiate or integrate any kind of curve. And that Euler's method was basically based on slope. But
Oh,
if we are gonna do it in a different way, so we have like lots of formulas, different formulas for different curves. There is this power formula, there is this derivation formula, like division formula is this, the log formula is this, and that formula. But for Euler's method, we have just slope. The same concept for the derivation and the same concept for integration. No need to memorize the long formula list. Okay, so the next section is about Euler spiral, and the third section is about the Euler formula. And
oh,
this is what our most important section is. And for this formula, we need to know about the the trigonometric ratios, the trigonometric identities like the sine and the cosine, which you have studied very well till now. And also we must know about the exponential functions, and then we must also know about the complex and the imaginary numbers. So for this formula, we're gonna learn about these three things, which the one you have studied very well, and then we are gonna turn into imaginary and complex numbers, and then we will learn the exponential functions, and then we are just gonna join them all together. Okay?
okay.
And then there comes this mysterious or like the mind-blowing Euler formula at the end. And
Mm.
then And then you will be very surprised to know that what Euler's formula make the shape. What is the shape of the Euler's formula? And I would seriously like to see your face at that time. Then when you will discover that, oh, actually this is the shape we are trying to make by these three very different concepts of mathematics. Okay,
Yeah.
so I will send you the link of the documentary on the Euler Leonard,
Okay.
and it is one of an American professor, the Dunhan. Yeah, the Dunhan is basically the name. I don't know the second name. So yeah, um, so I will send you the link of that, and if you will get a time, you can watch it, and if you didn't get a time, so we will watch it together. Okay?
Okay, I will try to watch it.
Okay, okay. So we will. Okay, what do you think about this timing?
This time is good. Yeah, this time is fine.
Okay, so we can have same like we can have next workshop at the same time on Friday and Saturday, Friday and Sunday.
Oh, actually, okay, तो अगर Friday पे होएगा तो फिर
Okay, and Saturday and Sunday.
Saturday and Friday, Saturday or Sunday में I usually go to the masjid. तो
Okay, okay.
रात में तो बेहतर है अगर early होएगा. लेकिन मैं
So
I Monday कर सकती हूँ. Monday कर सकती हूँ in this timing, and then
and
also um also today, like Monday and Wednesday, I can do this time.
okay. But the Monday I have with the Fatima as well.
तो अच्छा चलो तो फिर हाँ तो अच्छा तो फिर हम बस रख
तो फिर
I'll
हम
just
same time उस actually um um I will prefer getting up early rather than like sleeping
late.
late.
Yeah. Okay. तो फिर honestly
So it's fine. We can do on like on the previous timings as we were doing before. Okay?
okay actually we can do okay, wait, yeah, actually, sorry, sorry. So I think we said, what is it, like 10 or honestly, मैं 9 बजे भी कर सकती हूँ अगर आपको एहसान होएगा. Fridays पे मैं 9 बजे रात में कर सकती हूँ और आपकी I think आपका let me think 9 बजे morning में कर सकती हूँ. आपका होएगा I think probably 6 or 7 p.m.
It would be on.
Right, like Fridays and Sundays.
Okay. Can we like for Sunday? The 7 p.m. is fine for you for Sunday.
Um, Actually, yeah, 7 p.m. 7 p.m. should be fine.
Okay. And the next day, like any day on which 7 p.m. is fine for you.
Okay.
Except the Monday because the Monday and the Thursday I have with Fatima. So
Okay. Then
7 p.m. any day.
okay. I can do 7 Wednesday and Sunday is fine, actually.
Okay.
Or would you prefer Friday and Sunday? I think Wednesday and Sunday would be better because Friday पे मैं usually masjid जाती हूँ around like 6 p.m.
Yes. So
Yeah.
it's fine.
So yeah, Wednesday and Sunday are good days for me.
Okay. So we will have the same timing